we're going to discuss the thermal history of the universe. Uh, After the Big Bang, the cooling of the universe allowed the existence of different mixture of particles in thermal equilibrium. Uh, what happened to the particles is that could be form composites such as nucleons, nuclei, and atoms are able to form and survive. When the falling thermal energy KT could no longer produce various type of particle antiparticle pairs, the antiparticle annihilates with particles and disappear. So because there are more particles than antiparticles. Okay. And of course, that was also one of the particle physics and cosmology questions. Why should be more uh, particles than antiparticles? But anyway, so the antiparticle disappears. Uh, some particle decouple, we say, which means it ceases to interact with other particles in the cosmic soup. So form so-called, for example, the relic photons and the neutrinos. These are cosmic backgrounds particles. Uh, they cease to exist because the cross section typically comes so low. Determine what reaction took place to maintain each thermal equilibrium involve dynamic calculations, taking into account the reaction rates in expanding and cooling medium. The basic requirement for a given particle to interact is to be significant at a given epoch is that the time interval between particles scattering be much shorter than the age of the cosmos. This can be expressed as so-called a gamma condition, that the reaction rate must be faster than the expansion rate as measured by the Hubble constant. Uh, the big gamma is the reaction rate, H is the Hubble constant. The reaction rate is a product of the number density, velocity, cross sections. Uh, Number density times velocity is the flux of interacting particles. It's the number of particles passing through unit area per unit time. The cross section can be measured in the lab or predicted by theory. This condition can be used, in fact, to solve for the thermal energy KT and the redshift value Z at which a new equilibrium stage started. Okay, so later on, sometime we just give the result after some uh, dynamic calculation based on this gamma equal to H condition. So now we look at the pictures of the history universes pictorially. And here is, anyway, uh, basically it's a plot of the scale factor with cosmic time. So now it's here, this beginning universe. And notice the particular features. Uh, Once the uh, beginning, there's this big bang, then afterwards this afterglow of the light. That's the form of the cosmic micro background, about 380 years after the beginning. Okay. Uh, and then galaxies, planets formed, and then we are now in the stage it's dominated by so-called dark energy, and the expansion is accelerated. Okay, and one particular feature, this uh, the expansion is basically like a power law. Okay, and then start accelerating. And eventually, it's really actually begin phase of exponential expansion. But uh, most notice is that from t equals 0 to here, there's the age just exploded. You know, so this period is called inflationary epoch. Okay, and we can talk about some related to quantum fluctuations. Now we look at the same picture. Instead of time increase to the right, this increase from bottom to the top, and stressed out the, and basically will tell you where obviously we're not going to talk to every stage, but with a few stages we're going to emphasize. Uh, by the way, there'll be a list, a more detailed description on page 191 in chapter 9 about this chronology of the universe. Uh, in section 9.2, we're first going to talk about primordial nucleosynthesis or Big Bang nucleosynthesis, where the element deuterium, helium are first formed in the Big Bang. Okay. And then we'll talk about so-called photon decoupling, and also sometimes called recombination time, when the atom formed, so our charged particle got into the become neutral atoms, so therefore the photon cross-section suddenly dropped, and the unit became transparent to photons. So the relic photon radiation decoupled, formed so-called cosmic microwave background, which is section 9.3. Some minor details here. We'll talk about neutron proton freezes out, the ratio of proton neutron fixed as around 1 second after the Big Bang. And then also the neutrino get decoupled season, and that's more detail in box 9.2. And a few seconds later, the positron disappeared, and as a result, the photon get a boost of energy. That's worked out in exercise 9.1. In chapter 10, we're first going to talk about uh, so-called inflation cosmology. This relates to grand unification transitions. And before that, it's uh, quantum gravity, which of course we don't know. We don't have a theory of quantum gravity yet. Uh, then in section 10.2, we're going to talk about dark energy and dominating universe through the expansion accelerating until today. Okay, so this gives some idea of what sort of topic we're going to talk about. So that's the end of part 2 of lecture 25.